Use algebra 2. Hey, I've already told you this one. Pre-calc, I know that last year I taught regular pre-calc. I didn't teach the honors class because Denny teaches the honors one. The regular pre-calc class, for the first time I taught it last year, I would say about 80% of the material you do first semester is all review of algebra 2 that I teach. When you get into the trig stuff in your second semester a little bit, it's still a lot of review. It doesn't start really becoming new till almost halfway through second semester. So pre-calc is just all this algebra 2 stuff with basically one extra step. And I show you guys a lot of it as we get to it. I show you a lot of what we do next year. So multiplying, dividing radicals. Again, this is simplifying fractions. This is simplifying exponents. This is playing the games of war, things like that. It's multiplying things together. Power to power, you multiply. Same base, different exponents, you add exponents, things like that. How do you combine radicals? That's what we're looking at. For example, if I wanted to look at, I want you to figure this out. If I wanted to combine these things and leave them in the same terms, these two guys can't be multiplied together because they have different nth roots. I can't combine them. Whereas, what I mean by combining them, I can't put them underneath a single radical, okay? I can't do that because their nth root values are different. You probably already knew that. When I get to this one though, can I? Yeah. So I had the cube root of -4 times the cube root of 2. Well, since they have the same nth root, I can just rewrite it as one giant cube root. So what is the cube root? -8. -2, very good. Okay. This one I can't combine because the nth roots are different. A lot of this stuff is going to stem, literally, could you multiply the cube root of 6 times the square root of 2 on a calculator? Sure, but that means I'd have to let you use a calculator. Ooh, the plot thickens. I haven't decided yet. All right, let's simplify this. The cube root of 54x to the 5th. Now, just like we've done in the past, I've tried to keep you guys, I want to try to hold you guys responsible for knowing your perfect squares. We all know those, 1, 4, 9, 16, 25, and so on. When we get into the cube roots, perfect cubes, usually if you know up through 5, you're probably going to be all right. They're not difficult to work with. When you think about perfect cube roots, 1, 8, 27, let's forgot that one. And then 4 cubed is 64, I believe. And then 5 would be 125. 6, well, 6 isn't terrible. It's 36 times 6, which means it has to end in a 6, which is 16. Okay. Actually, it's 947. Thanks. I might use that one later because it could be close to 216. Oh yeah. Well, whatever. So, what's the perfect cube root that's hiding in a 54? 27, very good. I can rewrite this as 27 times 2, and then I have x to the 5th. So what's the cube root of 27? What's perfect? Yeah, remember how we'd say what? Okay. So what's the cube root of 27? What's the perfect cube root that's hiding in the 54? Remember how we would find perfect squares that are hiding? We do the same idea. So you take out the 27, you get 3. We have the cube root here. And then 3 goes into 5 how many times? 1, so I can take out 1, and how many are left? 2, so I have a 2x squared. And that's what it would work out to be. You simplify it very similarly like you would a regular square root, but you're using a cube root instead. You're looking for perfect cubes as opposed to perfect squares.
Why did you,
It's the shortcut stuff from yesterday. There's a couple of ways to simplify exponents.
I did watch the lesson yesterday.
Okay.
But I knew that that when there's exponents that you do, like how many times does that go into that? But why did you divide 54 by 2?
I'm looking for, when we're thinking about, when you had perfect squares, your perfect squares were 1, 4, 9, 16, 25, and so on. These were your perfect squares. Same idea, perfect cubes are 1, 8, 27, 64, 125. So if I'm trying to take the cube root of something in 54, is there one of these perfect cubes hiding within it? 27 was hiding in there. Because 54 is 27 times 2. Just like when we took the square root earlier of the square root of 12, what's the perfect square that's hiding in there was the 4, so you'd have a 2 root 3.
So you take it out so then you could take that out of the radical.
Yep. You simplify it the exact same way as you would the other one. Also, if you are trying to figure these things out and you forgot how to find perfect cubes, one of the other things you could always utilize, if you have your calculator, is your y equals. Yeah. Okay, yeah, I think I have it. I threw it on the charger. I thought you left it there for the charger. Yeah, go ahead, absolutely. So if I want to figure out a perfect cube root, oops, look at this. Is that all this stuff? So in your y equals, type in 54 divided by x cubed. That's what I'm saying. Well, a lot of these things you're going to find is you'll be surprised at how many of these things you'll pick up on real quick. Because they're not going to give you giant numbers. It's usually going to be 27, 64, if 125. All right, it's not going to be anything extraordinarily crazy. Stop laughing. What'd you do?
I've never actually heard it.
Calculator's talking. And then you just go to your table. You go to your table, and you're just looking for where does it work. So it's divisible by the cube by 1 cube, so that doesn't help. It's also divisible by 3 cube, so it's 3 cube root 2. This is a nice way, whether it's a cube root, 4th root, whatever nth root. If you ever want to try to simplify it out via the radical using your table, you just take that number divided by whatever your nth root is, x to whatever nth root power. Okay, and it works out. Excellent. Do I need to do this one too?
Yeah.
All right. Cube root of 128 x to the 7th. Let's simplify it. So we have to think about what is a perfect cube root that's hiding within 128? 64. Very good. 125 times what is 128? So here we wind up with 64 times 2. So what is the cube root of 64? So I can take a 4 out, and then 3 goes into 7 how many times? So I can take out an x squared, and what am I left with on the inside? I have my little cube root here then. And that's it. You're simplifying it the exact same way as you would a square root, but you're just looking for cubes instead. You use the same exact process.
By the way, 1.5 times 1.024.
There's the door. Nobody likes it. I'm joking.
Can't you tell?
Are you flinging stuff at me? I'm sorry. Oh. That was awful. I felt so bad. All right, so can we combine these two? Yeah. So let's write them all underneath 1/5 root. In doing so, we get a 5th root of, well, what's 8 times 6? 48. And then I have x times x to the 6th. And then y to the 7th. Okay? So what I'm going to do now is that I put them together, and then I try to see if I can simplify it. Now you have a small number here. We have 48. Which means the only value that could possibly have a 5th root that works with that is probably 2. Remember, 2's, you have 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. Does 32 go into 48 nicely? No. So there is no perfect 5th root that I can take out of that, but does 5 go into 7? Does 5 go into 7? So what can I take out via an x and a y? So if I take out one x and one y, what am I left with on the inside? Good. And that would be my answer. Okay? That's what we're looking at doing here, guys. We're looking at simplifying things through going this way. Okay? Not too crazy.
It seems too lazy to show it to us, and he's gonna be like, "That's all it is, guys. That's all
And then
it
the
is."
problems in the homework. And the problems in the homework are gonna be like super weird.
Division. What do you think we have to do with division?
Subtract exponents.
Well, before we do that,
You have to do the happy, and it has to move north or south. The unhappy one.
yeah, all right, but before we even do that, first thing I gotta look at,
That's not what you
well, I'm just trying to say something, Gary, and you're just, what's the first thing I have to, in order to be able to simplify these things, what's the one thing you have to first identify?
The root. And
The nth root. Is the nth root thing, is it the same? Yes. Since it is the same in both the numerator and denominator, I can write this as one giant fraction. So I have 48 x cubed y squared over 6x to the 4th y. And now, what do you think you're going to do? Simplify. Simplify like we did before inside the radical, and then try to simplify the radical. You're just basically adding an extra step to what we did a couple of weeks ago. So always start with your numbers first. What's 48 divided by 6? 8. So I'm going to move this down here, I'm going to get the cube root of 8 in the numerator. And now we play our game of war. Who wins, x cubed or x to the 4th? So what does it become? In the numerator or denominator? Denominator, good. And now we have x squared and a y. Y in the numerator, good. Now, inside that radical, is there anything I can simplify from a cube root?
Yes,
8. So what does this become? 2.
wait, what did you take out of
I took the 8 out, because 8's a perfect cube.
No, it's not. Oh, perfect. Yeah. It's not. Oh.
I love the snotty part of that too. No, oh.
No, it's not. I thought you meant perfect square rows.
Okay. You're not mad at me yet, right? I know you're probably working on it.
We're working on it.
All right. Try this one. I didn't say that.
You said it was simple.
All right.
This one doesn't have the nth root.
But does it?
It does.
Oh.
What is it always implied to be if it doesn't? If you don't see it?
2.
La puerta está aquí. IE, sorry, I'm not right.
Something about being weird.
All right, so let's see here. Wrote it as a big root. Let's see, you get 4/9. Excuse me. So what happens then is, think about the fraction. Is 4/9 a perfect square? Yeah, it's what? 2/3. So if I can take out a 2/3, now think about this. This is 1 over a and 1 over b squared, isn't it? So what would be the square root of 1 over b squared? 1 over b. So I can take the b here, and I wind up with then 1 over a. Sorry, that looks like a 9. Now you could do that, you could probably do that a couple of different ways. If you wanted to think about it in terms of exponents, if it's a b squared in the denominator, that would be a b to the -2 in the numerator. You with me on that? So if you had that as a b to the -2 raised to the 1/2, it becomes b to the -1, which therefore you take that out, you get that's where it becomes 1 over b. Not sure that. We're going to worry about this whole rationalizing here in a second. That's the, oh!
What is that?
This is when I hit my head sometimes. It's easy. Bush did this. It's easy. Let's rationalize. Yes, ma'am. No, because this is simple. We're not solving for x. Good question. Do you have to worry about plus minuses when you're taking square roots and things like this for this? No, because you're not solving for x. You're just simplifying. So that's not a worry, okay? Now, I want to go back and remind you guys about this whole crazy notion called rationalizing your denominator, which I know that you guys did a whole lot of last year when you had x root 3's, and 2x's from your 30, 60, 90 triangles and things like that, where us Mino geometry teachers said that, oh, no, au contraire, you can't have that as an answer. 1 over root 3 is not a legitimate answer. You had to rationalize your denominator. You had to multiply the top and bottom by something to get rid of the radical in the denominator. Correct. You multiplied, whenever you're rationalizing denominators, you're multiplying by some sort of factor of 1. You're trying to create some way to eliminate the radical. Root 3 over root 3 is just another version of saying times 1. So what's root 3 times root 3? 3. So your answer here was root 3 over 3. And this was a legitimate answer. It's the same idea when we get into this stuff here. We're also going to work on rationalizing denominators. We see this a little bit more. We're going to, you know how we've multiplied before with i's? We multiply by conjugates. You know, if it was 2 plus I, we'd multiply by 2 minus I. We created a difference of squares. We do this also sometimes within denominators with radicals. It works the same way. But let's worry about rationalizing this one through after we simplify. So, excuse me. Let's see, we wind up with, so we have the cube root 5x squared over 12y squared and a z. I need to make that bottom into a perfect cube. I have to figure out some way to multiply that out so that way I get rid of those cube roots. So there's a couple ways you can go about it. One of the easier ways to do that is to break the 12, break that number into primes. We all know that 12 is 4 times 3, correct? Now, one of the nice shortcuts to do this is if I rewrite, we'll leave the numerator up here. If I rewrite this as 2 squared, 3 to the first, y squared, oops. What I need to do is multiply it by something. All I did there was broke it into primes with exponents. I want to multiply it by some values of those exponents that makes all those exponents 3. So using your properties of exponents, when you have same base and you're multiplying, you add your exponents. Which means all I would have to do here is multiply this one by a single 2, 2 3s, 1 y, and 2 z's. Remember, when you have same base and different exponents, all you're doing is adding them. I want to create this to become 2 cubed, 3 cubed, y cubed, z cubed. That would eliminate all of the cube roots in the denominator. It would make it a perfect square, a perfect cube, okay? So in doing that, all I'm doing is playing this exponent game of how many more 2's do I need to make it a 3. So I have 2 to the first. How many 3's do I need? I need 2 of them. How many y's do I need? 1. And how many z's do I need? 2. Yes, sir. Then you do the exact same thing to the top.
What are you trying to do?
I'm trying to create the bottom here to have everything as a perfect cube. I want all of these exponents to equal 3. I have 2, I need 1 more. I have 1, I need 2 more. I have 2, I need 1 more. I have 1, I need 2 more.
Oh, for when you multiply, you're trying to make it.
Correct. Because I'm trying to turn that into a perfect cube underneath the cube root.
So then you can take it out.
Exactly. I'm trying to eliminate it.
Okay.
So what happens then, kind of ran out of space here. I have this numerator now of this cube root of 5x squared times the cube root of 2, 3 squared, y, and a z. I'm sorry, that's supposed to be z squared. Okay? That's my numerator. My denominator now, as I multiply that out, can I slide this up a bit?
Yeah.
Let's do this a little bit better. What I'm doing now is this denominator becomes 2 cubed, 3 cubed, y cubed, and a z cubed. By multiplying it by those other exponent values, I'm being able to create perfect cubes all the way through. If you go back and think about what it looked like with square roots, when I had the idea of 1 over the square root of 3, and I multiplied it by the square root of 3, that idea was that this was an nth root of 3 to the first, and I multiplied it by an nth root of 3 to the first, which created the nth root of 3 squared, which was just 3. In essence, it's the exact same thing, but here we didn't have to show all those steps because we knew the square root of junk times the square root of junk was just plain old junk. Here you have to break it into the exponents to make it work. It's just it's an extra step than what we've done in the past. It looks more complicated than what it probably really needs to be. Okay? So now your denominator just becomes 2 times 3 times y times z. 6yz. Okay. The numerator, I have the same nth root, so I can combine all that now.
So
I have 5 times 2 times 9, 90. X squared, y, z squared. And I don't believe, And the other thing that's nice is that once you start looking at this, you have 5 to the first, 2 to the first, 3 squared. Are any of those going to work out to give us a perfect cube root that goes into 90 at all? No. You're done. Break it apart into product. You guys remember, you've heard the terms product of primes, right? When you prime factorize stuff and you put things in with all their exponents. If you break your denominators into that for the nth roots, it's just it's a real clean way of doing it. Because we know what you have to add to 2 to equal 3. You just add 1. Right? That's how that stuff works. Shall we do another?
Wait, did you leave it like that? Or just
Yeah, you're done. Because now you're done. You got rid of the radical in the denominator, and there's nothing up here that I can simplify.
Is there like a quick way to figure out if a number is able to be cube rooted by 3? Because I feel like I would like get to this and then like try to figure out.
Well, if you look at this, when you have 5 to the first, 2 to the first, 3 squared.
Yeah.
Because these are all written in terms of their exponents already. Do any of them have a cube to it?
Wait,
Do any of them have a cube to them?
Oh.
It's 5 to the first, 2 to the first, 3 squared?
No.
So you know you're gonna be all right.
Okay. What, I was talking about the number, not like the number 90.
Yeah, oh yeah, same idea, because if you break it down in terms of prime, those are the prime factors of 90. 5 times 2 times 3 squared are all, it's already prime factored.
Yeah.
Since none of those have an exponent of 3, you know none of them are, and you can't simplify anything out.
Yeah. So you just like kind of look at all the factors. And
Yeah, so if this was, let's say this was a 15. If that was a 15, then I'd have a 5 and a 3, which means I would have 3 cubed, and that could have come out. That's what I'm looking at. But since all this stuff is written already in my prime factors, if you put everything in prime factors, it's very easy to tell whether or not you have got an nth root that you can take out. Okay. Yeah, another one here. Let's try another one. It's a little less complicated this time. Because 7 and 5 are already primed. So we're going to set it up the exact same way. What we're going to do is we'll set up in terms of one giant, or I'm sorry, prime factor out the denominator. But obviously 5 is already a prime number, so it's just 5 to the first. So I rewrite this. I'm going to have the cube root of 7x over the cube root of 5 to the first times y squared. How many more 5s do I have to multiply to make that exponent a 3? 2 of them. So I have to multiply the bottom, top and bottom by a 5 squared and a 1y. Okay with that? Because now if you look at the denominator, this becomes the cube root of 5 cubed times y cubed. The cube root of junk cubed is junk.
Are we gonna get to a place where we have to start multiplying like square roots by cube roots and stuff?
Can you multiply square roots and cube roots together?
No, so like, but I mean, they'd have to be like both in our answer.
Usually when they have the simple, I see where you're really worrying about a bad case scenario. Like you're worrying if like this was a squared up
Yeah.
top. Well, then you would just leave it as the square root of 7x times the cube root of 5 squared
Yeah.
y. I mean, that's all you can do.
Yeah.
So you wouldn't have to worry about that. So now, how much money is 7 quarters? It's $1.75, isn't it? Because 5 squared is 25. What? 5 squared is 25, right? 25 is a quarter, right? If you have 7 quarters, you have $1.75, so it's $1.75. $1.75.
Wait, are dollars and 60s or
Are dollars and 60s or 100?
Because you know how time is like 60 seconds, but like money is 100.
60 cents in a dollar or 100 cents in a dollar?
Yes, there's 60 cents. There's 60 cents in a dollar. Can I give you 120 cents? Will you give me $2?
Yes.
Wow. Oh my god.
I just get confused
It's okay.
with conversion.
About like 2 quarters and 30 cents.
Oh, duh.
I asked my dad about it yesterday and he didn't give me it.
And you're done. Okay. And you're done. It's okay. Nobody was paying attention. You're fine.
Wait, didn't that just go on recording?
If it now it's on the video.
No,
If it's on the video.
Try to remember. Actually, I think that's all there was. To be honest with you, I don't think this section gets to the multiplying conjugates yet. I want to. I want to save that one for. All right. So yeah, that was it. If I'm not mistaken, the Excel thing should be there. I,
Did you know?
No, I know.
well,
I can just not do my homework.
Comparing our pictures.
why don't you do this? Oh, I'm sorry. Yeah. Because let's see.
Oh my god, I have to do so many things to get here now.
So yeah, so 12. I think that's all I had for everybody else. Yeah. Is that okay? And that way, at least you're practicing it and you go from there. So. But yeah, is it in the Excel thingy? It should be. Can you actually open it?
Yeah, I did it.
Yay!
There's 18 questions.
And they were like 50.
Yes, I know there are 500 tabs and things you gotta open to get there. I get it. I'm sorry.